Until that, yeah.
Okay. Let's get started. That, of course, was the original theme song to Hawaii Five-0. That was the version that was on the TV when I was alive. And I was living in Guam at the time, so that was just a great show for us. Today, I hope, is the last boring lecture. We have to cover the basics of waves before we can get to the good stuff, the interesting stuff. On Thursday, we're going to talk about Doppler shift, Mach cones. We're going to talk about beat frequencies. And then next week, we're going to be talking about standing waves, longitudinal and transverse. And those, of course, are the foundation of music. And so things are going to get more exciting, but not today. Okay, not today. I'm still recovering from the cold, but I tested negative for COVID twice. I wanted to make sure. And so I'll keep my distance during the lecture here. Is someone willing to give us an opening prayer today? Volunteer up.
Our dear Heavenly Father, we are so grateful that we are able to gather together today and be able to learn about physics. We're so grateful for the opportunity we have to study in BYU and learn from Dr. Francis this morning. We ask you to please bless us that our minds will be clear and they'll be open, that we'll be able to understand what we are learning, and that Dr. Francis will recover from his cold and be able to continue in his responsibilities. We ask you to please bless us with the Spirit and all of the things that we do today. And we say these things humbly in the name of Jesus Christ. Amen.
So much. While I was homesick, I got online and found that they had just posted the student evaluations from last semester. So I got to spend some time reading about what you think of me. So I think it's only fair that I tell you what I think of you. I think you are just amazing, wonderful, special people. And it's not your fault. I blame your parents. I think they raised you right. As I've told you this many times before, I came to BYU thinking that I was doing the good Lord a favor, and it turns out that it was the opposite. That my association with you has brought so much joy to my life that it's like this old man can keep on living. Oh, thank you for that. Thank you for that. We are going to start with a review today of where we've been a little bit. Well, let's start with this problem here. We have a 2 kilogram block. It's oscillating on a horizontal frictionless surface with a period of 1 second and an amplitude of 10 centimeters. And we want to find the spring constant K. Now, I hope you remember from last day that we have 2 methods now that we can use to find a spring constant. One we call the static method, and the other one we call the dynamic method. So let's, if we're using the dynamic method, we want to use this formula for the period of oscillation. With the dynamic method, we get a mass on that spring and we get it bobbing up and down. And we measure how long it takes to make one complete cycle. And then with that formula, we can solve for K. We're also asked in this problem to find the maximum acceleration of the block. And anytime you're looking for an acceleration, you should immediately go to that Newton's second law, F net equals ma. That's always going to be your go-to equation there. Let me get some board space here. Okay. So if we're using the static method, we take a spring and we hang a mass on it and we measure how much that stretches the spring. And then we use Hooke's law. And you notice I left out the minus sign there. Okay. For the dynamic method, we start with this formula for the period. And we solve it for K. And we first of all square both sides. And then we cross multiply and we get K is equal to 4 pi squared m over t squared. Well, I told you last day that pi squared is about 10. And so this is going to give me 4 times 10 times the mass. It was a 2 kilogram. I'll leave off the units here. And the period was 1. And when you square 1, it's still 1. And so that's going to give me 80. And the units here for K are going to be newtons for each meter that you would stretch that. And so that would be the answer to the first part of that question, 80 newtons per meter. Questions on that, what I just did? Does that make sense? On the exam, you'll be asked to find a spring constant with the static method and also with the dynamic method. In this case, you clearly didn't have enough information that you could have used the static method. You had to use the dynamic method. Now, the second part of this problem is asking us for the maximum acceleration. And we know that that maximum acceleration happens at the turnaround points, okay? If that's equilibrium, then I pull that out some distance A, and I let it go. And it's going to bounce back and forth from plus A to minus A to plus A to minus A to plus A. And so the acceleration is going to be greatest when the force on that block is the greatest, and that's when the spring is either stretched the most or compressed the most. And so the net force is equal to the mass times the acceleration. And the net force in the case of this block, the weight is canceled by the normal force by the table. And so the net force is just the spring force, which is K delta F, MA. Now, if I want that A to be the maximum A, then I want my delta S to be the maximum delta S, which is A. And so if I solve this for A max, I'm going to get 80 newtons for each kilogram. No, 80 newtons per each meter, sorry, times 0.1 meter, that's 10 centimeters, and I divide that by 2 kilograms, and that's going to give me 4 meters per second squared. Check on your neighbor, see if your neighbor's still on the bus there. Are there questions? Yes, sir. Where did I go from A to S? Uh, The formula for the force by a spring has a delta S in it, okay? K delta S. Delta S is how far the spring is stretched from its equilibrium position. And when it's here, that might be 1 centimeter. Here it might be 2 centimeters. Here it might be 3 centimeters. Here, it happened to be 10 centimeters. And that's the biggest it was ever going to get. And we gave it a special name, A. So I just plugged in A.
Like doing like.
You know, we're just looking for the magnitude here. I leave out the minus signs in the Hooke's law just to get rid of minus signs.
I didn't know.
The force is biggest at either turning point. It's going to be equal to it's going to be equal to 8 newtons here to the right, and it's going to be 8 newtons here to the left. Anyway,
It's just the answer.
right, just the direction changes. 0 in the middle at equilibrium because the net force is 0. Okay.
Sorry. I'll say that. So listen to us.
Ooh.
No, it'll be good.
Okay, we've been here before. When we talked about energy in Physics 105, we found that we could define energy buckets because energy was a scalar quantity, not a vector. It doesn't have direction. There's no such thing as 60 joules east. It's just 60 joules of energy. And so like paint, we can put it in buckets. And we can define a kinetic energy bucket. We can define a potential energy gravitational bucket. And we can define a potential energy spring bucket. And you remember energy was just the capacity to do damage. And a spring, if it's stretched or compressed, has the capacity to do damage. Now in this system with a block attached to a spring going back and forth on a horizontal surface, the only buckets that make any sense are the kinetic bucket and the spring bucket. I can always define that height of the table as 0 to get rid of that gravitational energy. And we know that if we add those two buckets together, we get something called the total mechanical energy bucket. It's just the sum of the kinetic plus all potential. And as this thing goes back and forth, you see that the two buckets slosh the energy back and forth. But the total energy, the mechanical energy, stays the same, assuming, of course, that that surface is frictionless. And we are always going to make that assumption in this class. In upper division classes, they put friction in there. It becomes a very messy problem, but it's a very important problem. But we're not going to deal with that here. Now, what that means is that we can use that total energy and the fact that it doesn't change to solve a lot of problems. And you will be solving a lot of problems, both in your homework and on the next exam. At the turnaround points, the block has to stop to turn around. And so all of the energy is going to be in that potential energy spring bucket. And in that case, my delta S is going to be A, the amplitude. At the equilibrium point in the middle, all of the energy is in the motion of the block because the spring is neither stretched nor compressed. And then when I get to the other turning point, all of that energy is back in the spring bucket. But the total has to stay the same. If I add those up together, that has to equal that added together, has to equal that added together. And indeed, any point in between, any point in between. Now, you had a problem on that first homework assignment, problem 5, where you were told that a spring went back and forth with an amplitude of 16 centimeters. It went from negative 16 centimeters to positive 16 centimeters, back and forth, back and forth. And you were asked some questions about, you know, how fast is it going when it's only 12 centimeters away? You got a different number. Every student got a different number, but, you know, let's see how we would solve that. You're going to have several of these problems on the next exam. And the first step is always, every single time, find the total energy. Okay, find the total energy in the system, because that's what stays the same. That's what's conserved. That's what you can count on. And the general formula for that, that total energy is just this. It's just all the energy that's in the motion of the block and all the energy that's stored in the spring. Okay? And that always applies. Whether you are at turning point, whether you're at equilibrium, or whether you're in between. That always applies. Now, if you are at a turnaround point, this general formula becomes a little simpler. Because the block has to stop to turn around, this term goes to 0. And because at the turning point, delta S is equal to the amplitude, I can replace delta S with capital A. Okay? Now at equilibrium point, at this center point, again, the general equation becomes simpler. Because the spring is neither stretched nor compressed, my delta S is 0. And so I don't have any energy in the spring bucket. All of the energy is in the kinetic energy bucket. And so that means the block's going to be going the fastest it's ever going to be going. That's the maximum speed, is right there in the middle. Now, in this problem, the first thing you want to do, even if we're not asked for it, even if there's no points assigned for it, is we find the total energy of the system. In this case, we were told that the K was 100 newtons for each meter, and the amplitude was 16 centimeters, or 0.16 meters. And so if I plug that into, well, which formula should I use? Which of those three should I use? Yeah, I've got all the information I need for this one here. And so if I plug into that one, I get 1.28 joules. And with that information, you are all powerful. I can ask you, how far away from equilibrium is this block when it's going 2 meters per second? I can ask, when it's 12 centimeters from equilibrium, how fast is it going? Okay, all sorts of questions can be answered once I know that total energy. See if your neighbor got this problem right when they did the homework. Do a buddy check again.
Está bien. I thought there was. Yeah.
Pretty much. 100%, by the way.
They all say.
Okay,
Doesn't. It's on
so here we have a problem. A 2 kilogram block is at rest at the end of a horizontal spring with a spring constant of 100 newtons per meter. The block is pulled out 20 centimeters and released. What is the maximum velocity of the resulting oscillations? Well, I know that kinetic energy is 1/2 mv squared, and the maximum potential energy is 1/2 k a squared. And so with that information, find out the fastest this thing will ever be going, the maximum speed that this block will have. With your neighbor, get me an answer. We're going to use your clicker in a minute.
Kinetic energy. Yeah. It's 2 joules. Yeah.
Okay, when you get an answer, share it with your clicker.
I don't think.
Yeah.
I don't know. I don't have a calculator. I press. I saw the sun. You have voice recognition. There's no way I'll need it. Until get back into physics. Like a 1,000. Forever, like it's forever, and yeah, I'm pretty sure they're probably, but I mean, I would expect. No, I thought.
Okay. That should have been enough time. Last call, get your vote in.
Yes.
Okay. They tried to put this class in a room that is over in the science center that holds 170 people, and that would have been bad. Okay. Let's see how we did. Good. The answer is A. Very good. Very good. Okay, and here's the reasoning. The first step, of course, is to find the total energy. I can find the total energy by using the potential energy at the turnaround point, and I get 2 joules of energy. I then put all of that energy into the kinetic energy bucket at the equilibrium point to find the maximum speed. And I solve for that maximum speed and I get 1.41 meter per second. So the answer was A. Okay. Questions on that? Just a little bit of algebra is all. Okay. Key concepts so far. The period, we use capital T, and that represents the time, the period that it takes to make one complete cycle, depends only on K and M for a mass on a spring. The spring constant can be found two ways, either with Hooke's law, the static method, or from the period of oscillation, the dynamic method. The maximum acceleration can be found with Newton's second law. And indeed, any acceleration can be found with Newton's second law. And the amplitude and the maximum velocity can be found with energy, So those are the key ideas. Ah! Did you hear that back there? Did you smell my bad breath? No, they did, but you did not, okay? And that's the idea behind a pulse, okay? A pulse is a traveling disturbance. There was energy and momentum that went across the room and assaulted your eardrum, okay? Banging on your eardrum. But the medium, the air, didn't go back there. The air that came out of my mouth didn't go back there, okay? You did not smell my bad breath back there. It was the disturbance that traveled through the air to get to you, okay? And these pulses come in two flavors that we're going to talk about today that are very, very different. The first type we're going to call longitudinal, and that's where the bits of stuff that are carrying the pulse move along or parallel to the direction of the energy flow. In other words, as I made that pulse go to the back of the room, the energy was going that way. And that meant that the air molecules that were carrying that pulse were going back and forth parallel to that direction. I can demonstrate a longitudinal pulse with this slinky. You can do a whole lot of things with a slinky. Slinkies are useful. Okay. If I pull this back right here, I make a compressed region and a rarefied region. And if I let go, that compression moves from your left to your right. Okay. And then it bounces back. Don't worry about the bouncing back. We'll get to the bouncing back this week in tutorial. Okay. Now, if I think of these dots as different parts of the slinky, or as molecules of air, it's the medium that carries the pulse. And the arrows represent the equilibrium position for those objects, whether they're rings of a slinky or whether they're molecules. That's their happy place where they want to be. And if I disturb that on the left, it disturbs its neighbor. And there has to be some connection between neighbors, some way of passing along the information, kind of like gossip in a small town, okay? And so you see that the displacement of that first object has already moved this one away from equilibrium. And when it gets the furthest it's going to get from equilibrium, I turn it blue. And what you see is that the place where it's the maximum from equilibrium travels across the room. But the individual objects don't travel across the room, okay? Just the energy and the momentum travel across the room. Now, a transverse pulse, the bits of stuff that carry the wave, the pulse, move perpendicular to the direction of energy transport. And I can demonstrate that with this wave machine from Bell Labs. What we have are a bunch of metal rods, and these rods are tied together by a wire that essentially tells each rod what its neighbor is doing. When I lift this rod, I twist the wire a little bit, and it causes the neighbor to be displaced. And so if I make a pulse by lifting this up, that pulse travels across. And don't worry about the reflection back. We'll get to that in the tutorial this week. Okay. So in that case, I can show that graphically by objects that are displaced from equilibrium. In this case, that horizontal line is equilibrium. And you see that the pulse travels from left to right. Okay. Now, what's important is the speed of the pulse. And that's just how fast I would have to run to just keep up with that pulse as it moves across the room. That's that simple. Now, it turns out that for transverse pulses, and these are pulses that are on a spring, a string, a wave machine like this. These are the pulses that we're going to be working with in this week's tutorial. The speed of that transverse pulse depends on two things. The restoring force, in this case, the tension of a spring, and the mass density, which is the inertia, or how hard it is to make that spring speed up or slow down. Now, how do I make that visual? So imagine that we had a whole bunch of football players up here from the football team. Okay. Do we have any football players that are on the team in the class? Oh man, I'm sure proud of them. Really? That's amazing. That was amazing. Let's give them a hand, everyone. Yeah. Okay. So all these football players are up here holding hands, and one of them jumps up, and in the process lifts his neighbor, who lifts his neighbor, who lifts his neighbor, who lifts his neighbor, who lifts his neighbor. Now, the speed at which that pulse is going to travel across the room depends on how hard they're pulling and how hard it is to speed them up, how heavy they are. Okay. Now, if I think of a spring as it's a continuous thing, it's not the total mass of the spring, but it's the mass per unit length. Okay, how much each meter of the spring, how much mass it has. And that's what we give this symbol mu to. Okay. Now, again, we have to solve a messy equation to find this result, and we're not going to go there, but the result is the square root of the tension force in the spring or string divided by the mass density of the spring or string. Okay? So that is the speed at which it will travel. And that formula will be on the front page of your exam. Now, the pulse speed for sound, that is a longitudinal pulse, that what we find there is that it depends on the average particle speed, which depends on the temperature of the gas that it's going through and the mass of the particle that makes up that gas. And nothing else. Nothing else. Now, there's a formula for that we're never going to use. Okay? It's a formula that, again, would be very difficult to derive with some mathematics that we don't have in this class. But all we're going to use in this class is that it's about 343 meters per second at room temperature, and room temperature we do in Canadian, okay, 20 degrees C, okay, Canadian. It turns out that as you heat up the room, as this lecture goes on, and each of you with your little heater generator, your bodies are generating 100 watts each, you're going to heat up this room, and that means they're going to speed up sound by 0.6 meters per second for each 1 degree C that you raise the temperature in this room. And that means that the lecture is going to go a little bit faster at the end of the hour.
Yes.
Okay. Here's the formula that we're never going to use. And it's kind of messy because that T is temperature in Kelvin. And this K is not the spring constant that we've been talking about. It is Boltzmann's constant. That's a number that I hope you never need to use in this class. Okay. So we will never use this formula here. I just want you to see that it only depends on temperature and the mass of the particle that is making up the gas. Now, because it depends on temperature, we have a phenomena called refraction. And that is that, you know, back in the day when you were out on the blacktop and you were shouting to your friends over there, "Hey, everybody, wait for me, I'm coming." And they pretended they couldn't hear you. Okay, they pretended you didn't exist. I know that never happened to me, but maybe it happened to you. Okay. In truth, they didn't hear you because the air was really, really warm next to that blacktop. It was cooler up here, and the sound travels faster in the warm air. And so that means that these wave fronts, these compressed regions, are going to essentially bend up above your friends. And so they weren't ignoring you, they just didn't hear you. Okay. On the other hand, when you're out hunting for elk in the snow, the air is cooler next to the snow than it is above. And so every little sound that you make is going to come right back down and alert the elk. Yes, sir.
Can you explain again why?
That's not an elk. Yeah, I know.
Can you explain again why it refracts towards cooler air? So
If I have a lawnmower, and this is the old style lawnmower that you had to actually push. Okay. If this wheel is in mud, going slow, and this one is on concrete or the driveway, going fast, this thing's going to turn. Okay. And these lines here represent compressions.
cold air.
Compressed freeze, we call them wave fronts. Okay. Yeah. And so since it's that's the pulse. That's the pulse. And so since they're traveling faster towards the ground on the top picture, they're gonna turn like the lawnmower. Okay. Okay. This is a problem, an example in your textbook. A steel wire of mass 0.3 kilograms and length 0.6 meters supports a 100 kilogram block as shown. The wire is struck exactly at the midpoint, causing a small displacement. How long does it take that displacement to reach the top of the wire? Well, first of all, why does it go up? instead of down? Tell your neighbor, why does it go up instead of down?
It's down and down myself.
Actually, really straight.
I mean, I don't want to. Yeah.
I mean, that's all.
I don't even know if the.
But we.
It's about the wire.
That's
It's like.
like-
Where's he gonna go?
Obviously, it's additional.
Okay, of course, the answer is that it goes up and down. There's no reason for it to go one way over the other. Just like when you throw a rock into a pond, the ripple goes out in all directions as a circle, okay? So, but we're just asked to look at that one that goes up. And so I know that if I'm trying to figure out how long it's gonna take to get to Denver, I just use the V is equal to how far I gotta go divided by the time. And that gives me the time is just how far I've gotta go divided by the speed. Okay. Well, if I'm only going from the middle to the top, I'm only going 0.3 meters. The whole wire is 0.6 meters, but I'm only going half that distance. So my answer depends on what the speed is for this pulse. And we just talked about that. The speed was equal to the square root of the tension divided by the mass density. Well, if I draw a free body diagram for the block, the weight of that block, if I use 10 for the gravitational field strength, would be 1,000 newtons. And that means that this tension force is going to be 1,000 newtons. Okay? And so I've got part of it. But now I need the mass density, linear mass density, and that's going to be the mass of the spring, or in this case, the wire, divided by the length of the wire. And that's going to be 0.3 kilograms divided by 0.6 meters, and that's going to be 0.5 kilograms per meter. So I plug that in here, 0.5 kilograms per meter. And if I plug that into my calculator, I get about 45 meters per second. And then if I plug that in here, I get 0.0067 seconds. Okay, and that's in your textbook. That's example 1 in chapter 12. Okay. And remember, chapter 12 I posted to the MAC site for those of you that are still waiting for your textbook to arrive, but I can't do any other chapters after that for copyright reasons. Okay. Questions? Just a straightforward plug and chug problem.
Not just between.
To find the mu, you mean? Well, the mu, whatever length I want to use, I got to use the mass for that length. And since they gave me the mass for the whole length, all 60 centimeters, I have to use all 60 centimeters. Yep. Okay. Okay. What about reflections? If I use this little clamp here, this little alligator clip to essentially hold down this last rod so that it can't move, what we find is that if I send a pulse along this machine on top, when it reaches the boundary, it will reflect back on the bottom. So watch what happens here. It comes in on the top and it comes back on the bottom. Now, if we think of those football players again, okay, each of those football players pass the pulse along by lifting their neighbor, lifting their neighbor, lifting their neighbor, lifting their neighbor. And then we get to Fred. He's the one at the end, and he's holding on to the wall, the door, okay? And when he goes to lift his neighbor, he can't lift the wall, and so he pulls himself down. And then he pulls his neighbor down, he pulls his neighbor down, and that's how we get that reflected pulse, inverted, okay? Now, it makes sense that that speed at which that pulse travels depends on the mass. Instead of a bunch of football players, imagine I had a bunch of ballerinas. And in that case, it would just, okay? It wouldn't take very much to lift them out of the way of the pulses, and it could go quickly across the room. Okay, new topic. Let's play a game that you played in Sesame Street. One of these things is not like the other. I've got two lists here, and the list on the left is very different than the list on the right. So with your neighbor, discuss what is it about the list on the left that makes it different from the list on the right. Talk to your neighbor.
We're the same.
Yeah, what about like involved?
All of them.
They both have pattern.
Whatever it is that you're like, it seems like they're reading.
They're all like red. Have a page, link.
But like happened in like. On that other side, I don't know what you're on. I don't know what it is. Yeah, I don't know.
Just like a singular event.
Right, don't even see.
If you've got the same thing.
Try to even get hit by 1.5. Quicker.
But on this one, multiple. Same thing.
Pattern.
Okay, brave soul, where are you? Raise your hand, brave soul. Yes, sir. Okay, so the one on the left are all in the same place, is that what you're saying? Oh, okay, so they're static, okay, the ones on the right are static, they're not going anywhere, but there's motion on the left. Okay, but they're in the same location, okay, so any other?
These ones are separated by time and those ones are separated by space.
Say it louder, please.
These ones are separated by time and those ones by space.
Okay, good. We're saying the same thing, but in different ways. Here we have repetition in time, and here we have repetition in space. Okay, here the flashing traffic signal, it's always in the same location, but we repeat something, in this case, the flashing, in time. Whereas here, the telephone poles, they repeat every so often down the road, but there's no motion, okay, repetition in space. Okay, it turns out that for waves, they result from a periodic disturbance. I'm going to unclip this. Instead of sending one pulse down, if I keep on disturbing it in a periodic way, I can send a wave across. A wave is just a collection of pulses, one after another, created by a periodic disturbance. And I can always count on the fact that this wave is going to have the same period and hence the same frequency as the thing that's creating it, the disturbance that's creating it. Because every time I make a pulse, it takes off. Okay, and so the frequency at which those pulses arrive somewhere else is going to be the same as the source. It's characterized by the amplitude, how far the bits, in this case those rods, move from their equilibrium position. It's characterized by the period or frequency at which they go back and forth or up and down. And that looks familiar. That's what we characterize, that's how we characterize simple harmonic motion. Well, here's the new stuff. This is the extra, and that's the wavelength. And that's going to be the distance over which the pattern repeats itself. In this case, it would be from crest to crest, from one crest to another crest, or from trough to trough. Okay? And the speed, it should not surprise us that since a wave is just a collection of pulses, the speed of a wave is going to be exactly the same as the speed of a pulse. If I've got a wave going on a spring or a string, it's going to be given by that formula that we just used, the square root of the tension divided by the mass density. If it's going to be a sound wave, that's a whole bunch of pulses going across the room. But they're going at 343 meters per second. Okay? And you wouldn't, I'm an old man. I've been around the block a few times. And the number of times I've been asked, oh, what formula should I use to figure out how fast that sound is traveling? The formula is 343. 343. Okay, so a wave is a repetition in both space and time. In space and time. So let's break that up. If I, first of all, just freeze time, if you were to take out your camera and just take a pic, don't really do it, but just take a picture of that as it's moving across, what you would get is something that looks like a sine wave. And from that, you could define the amplitude, and you could also define the wavelength. The wavelength would be from crest to crest, or from trough to trough, or from equilibrium to equilibrium. When you use equilibrium to equilibrium, you've got to be a little bit more careful. You've got to go from equilibrium going up to equilibrium going up. You can't go from equilibrium going up to equilibrium going down. It's the length over which you repeat the pattern, a full cycle, okay? So that's by freezing time. Now, what if and these wavelengths, I think of, this is useful, I think of them as boxcars on a train, okay? And all of those boxcars have the same length, and so I can think of that as the wavelength. We use the Greek letter lambda for wavelength. It's the Greek letter L, lambda, okay? And so each of those waves would have a wavelength of lambda. And the units, well, what units would you measure a boxcar in? The length of it? Well, the meters. And this wavelength is a length, so it would be measured in meters, Okay. Counting boxcars is like counting waves. If instead I were to tie a ribbon around one of these bars and just plot its motion as a function of time. Okay. A moment ago, I froze time and I was looking at all space. Well, now I'm going to freeze space and only concentrate on this bar that has the ribbon on it. And I'm going to look at all time. And as the wave goes past, I'm going to look at what that one bar, the one I tied the ribbon to, is doing. And what I would find is that it goes up, and then it goes down, and then it goes up, and then I get tired of collecting data, so I just don't take as much. But if I didn't get tired and I was more diligent, I would get something that, again, looks like a sinusoidal function. Now, in this case, I can find the amplitude and I can find the period. The period, since this axis here is time, this is seconds, okay? How long it takes to have one cycle. And I can go from crest to crest, or from trough to trough, or from equilibrium to equilibrium. Now, where on this picture do I find the wavelength? Where do I find the wavelength? I don't. Trick question, okay? It's not there, okay? And that's why you need both. You need both the spatial repetition and the temporal repetition. So in summary, when we freeze time by taking a snapshot, we can find the amplitude and the wavelength. If we follow a single point, if we freeze position, we get the amplitude and the period. And this gives me the spatial repetition. This gives me the temporal, or in time, repetition. And we need both. We need both. Okay? Now, I have an exercise again from your reading. We'll use our clickers for this. You've got a transverse wave that is traveling along a spring, and we've marked points A and B with pieces of yarn. And we just took a picture of the spring as this wave was traveling to your right. Now, if instead of taking a picture, we had taken a video, okay, how would each of those pieces of yarn, the one at A and the one at B, be moving at this instant in time? Would A be going up and B down? Would A be going down and B up? Would they both be going down, both going up, or A left and B right? Now, first off, I want you to see that this is a transverse wave. That means the pieces that carry the wave have to move perpendicular to the motion of the energy. That means they have to move up or down. That means E is silly talk, okay? So no one choose E. No one choose E, but with your neighbor, decide what it is and then use your clicker.
Yes. I got it. I was first. Mine says first.
Wait, it's already passed. It's back on its way up.
Yeah, like my boat.
What's
Yeah, I think it's.
Yeah, that's like fall with the line.
That straw. It's like, and if it'll be down. He's gonna move up. Yeah.
Okay, get your vote in. Get your clicker point. Last call. Ooh, we're not sure. We think it's either A or B there. Okay. Let's do this together. It's important to think of this as a movie. If I waited a tenth of a second, the wave, the disturbance is going to move to the right. And now the spring is going to make this shape with the dark line. Now, the pieces of yarn that I've tied to the spring, well, they have to stay on the spring. And it's transverse wave, and so they have to move either up or down. So that means that the one at A, to stay on that spring, has to move up, and the one at B, to stay on the spring, has to move down. So A goes up, B goes down, and so the answer is A. Now, another way of thinking of it is the spring, the parts of the spring move to let the pulse go through, okay? B is at the beginning of the pulse, and so in order to get out of the way for the pulse to travel through, it's got to move down out of the way. Well, A's on the tail end of that pulse, and it's going back to equilibrium. The pulse has already passed A, and now it's going back to its equilibrium position, so it's going to go up. Check with your neighbor, see why your neighbor got that wrong.
Wave shifts.
Thank you for your service.
Right.
Okay,
For most of it, I was thinking.
You'll have to go down. And again, not
another clicker question. If the speed of a wave on a spring remains constant, but the wavelength is decreased, what happens to the period? Does it increase, decrease, or stay the same? With your clicker.
Wavelength increase on possible.
Yeah, that would make sense.
Oh, wait, no, it goes up.
Got it, bigger than that.
Yeah, maybe. Smaller, it's gonna have to be faster.
So what's the difference? Like.
Okay, get your vote in. A, B, or C.
Then it would take less.
Okay. Okay, the answer is B. If I think of these wavelengths as boxcars, I can think of this as two trains coming towards me at the same speed, 30 miles an hour. I'm standing right between them. The period is how long it takes for one boxcar to travel past me, okay? And if the boxcars are shorter, it's going to take less time for them to go past me if the two trains are going the same speed. So the answer is B. Now, we have about 7 minutes left for the class, and I want you to see this problem here. there's a problem here that's very much like your homework. But before I get to that problem, I need to give you the grand high wave equation. You see waves rolling onto the beach and estimate the wavelength at about 3 meters. You measure the time between the wave crests at 2 seconds. What is the speed of the waves? Well, okay, you're at point B, and you've done this before in the waves. You jump up so that the water doesn't go over your head every time a crest comes towards you. You've just jumped up, and it takes 2 seconds for that crest at A to get to you at B. Okay. And so how far did it travel? It traveled 3 meters, and it took 2 seconds. So what's the speed? It's going to be 3 meters divided by 2 seconds. Okay. 1.5 meters per second. Now, how did I get that? Well, I divided the wavelength by the period, and don't write that down, because that's not the form that we usually use for the wave equation. We know that frequency is 1 over the period, and so I can write this as the speed is equal to the wavelength times the frequency. Now, folks, this is the grand high wave equation, the one equation to rule them all and in the darkness bind them. This is the F net equals ma of waves. This will be the equation that you will use more than any other equation this week, next week, on the exam. Okay. Now, this is the homework problem. This is very similar to your homework problem. And when I say similar, what I mean is the same. Okay, the same. The amplitude of a transverse wave is 1 centimeter. A particle on the string moves a total distance up and down of 12 centimeters in 1/10 of a second. If the wavelength is 1.5 meters, what is the speed of the wave? Well, let's look at this. There's the transverse wave. It's got a wavelength that we're told in the problem is 1.5 meters. Okay. And we would like the speed of that wave as it moves to the right. Now, we just learned the wave equation. The speed is going to be equal to this wavelength, 1.5 meters, times the frequency of the wave. So what we want to know is, what's the frequency of that wave? How many waves go past this point right here in 1 second? Well, we know that each time we go from equilibrium to the crest, we travel 1 centimeter. And we've been told that we go up and down, up and down, up and down 12 centimeters in 1/10 of a second. So let's follow this little particle as it stays on the wave. How far has it moved? 1 centimeter. That's the amplitude. Okay. Now, how far has it moved now? 2 centimeters. 1 down, 1 up. Okay. How far has it moved now? 3 centimeters. Okay. And how far has it moved now? 4 centimeters. And 1 wave has gone past. So every wave that goes past moves that particle up and down and back up a total of 4 centimeters. I'm told that it moves 12 centimeters in 1/10 of a second. How many waves go past for 12 centimeters? 3. Okay. So it's moved 4 centimeters for 1 wave. How many wavelengths to move at 12 centimeters? That would be 3. And we're told that it makes 3 oscillations, 3 waves in 1/10 of a second. So how many waves would it make in 1 second? 30. Okay. So if I divide the number of cycles by the number of seconds, I get 30 hertz, 30 cycles per second. And so now if I use that wave equation, I was told in the problem that lambda is 1.5. I just figured out that the frequency was 30 hertz, and that gives me 45 meters per second. that is the hardest problem in the homework that's due on Friday. And that's the problem. That's the problem. Okay. Check with your neighbor, see if your neighbor's okay. Now, don't go anywhere. You still paid me for 3 more minutes. Sound, we said, is a longitudinal wave. That is just a series of compressions and rarefactions. And I can represent it with this visual. This is a diaphragm in your speaker that's creating compressed regions that move down the tube, okay? Now, you'll see that the energy is moving from left to right. But if you just look at one of those particles of air, it doesn't move very far from equilibrium. We call these places where they're bunched up the wavefront. The wavefront, that's the compression, and it carries the energy and the momentum, okay? But the vibration of an individual particle is not very far. Now, I want you to, do you hear a buzzer? I do not. That is my curse, okay? Now, if I pump all the air out of that chamber, that's the buzzers down inside that chamber. You can't hear it now? Well, I still can't hear it. Okay. What that means is that in outer space, no one can hear you scream. Go to the devotional. That's President Reese and his lovely wife.
So have you?
Yo, Alex.
Actually, I only have one flex.
Thanks for